In this video, we'll be looking at the long-term behavior of a transition matrix and of a state vector. So we'll start with what we've seen in the last example. So if I have a probability vector, we'll call it a steady state if it's not changed by p. So is steady state if when I apply p to q, I get q again. So we need two things. First thing, if you look at this, one way we would say it, it's an eigenvector for lambda equals 1. So Q's in the eigenspace of 1. There's an extra condition. I'm not allowed to pick any eigenvector I want because we have this word here, probability vector. So if Q is A1, A2, and so on, I'm going to ask that A1 plus A2 plus AN equals 1. All right, remember state vector represent the probability of each of the states. So if I have a sum of 1, that just means that there's 100% total probability of being in any of the states, in being in a state, I guess. All right, it's not true that every transition matrix is going to have a steady state, but as long as it has one extra characteristic, it will. So here's the extra condition that we have to impose on our Markov chain to make sure that we'll get a steady state and that we can look at the behavior as n grows to infinity. So we need a transition matrix is called regular. If p, or any power of p, has all non-zero entries. Now, since P is a transition matrix, the entries are actually going to be positive, so it has only strictly positive So starting anywhere, you'll always be able to reach every single state with non-zero probability after n steps, n events. All right, so let's try a couple of examples of this. I'm going to look at two matrices. I'm going to look at first matrix, I want to look at 1, 0, 0, 1. I'm sorry. That would work as well, but it'd be a bit more boring, so let's take this one instead. If I look at P itself, it has 0 entries, so P at first glance doesn't need to be regular, but I have this option here of looking at powers. As long as one of the powers has only positive entries, I'm fine. So let's look at P squared. I'm going to get 1, 0, 0, 1. I get the identity matrix. Still has 0 entries, so we haven't proven it's regular yet. But now I'm starting to think maybe it isn't. If I take P3, that's going to be P2 times P, and P2 is the identity. I get P. In fact, any odd power you could write like this, and so you get I2 to the K, P, that's just I2 K, so I2 P, which is P. So all odd powers will be P, and all even powers will be the identity. Both of these matrices have 0 entries. And so you'll never be able to find a power that has strictly positive entries. So all of these have 0. So that means P is not regular. Second matrix, I'm going to look at P equals 2, 4, 1, 0. So 2, 4, 1, 0. Again, it has a 0, so we don't know right away if it's regular or not. I'm going to start taking powers. P squared, 2, 4, 1, 0 times 2, 4, 1, 0. I'm going to get 8. 8 again, 2, and 4. I don't have any zeros here. So they're all bigger than 0. So as soon as one of the power has only positive entries like this, we know P is regular. So why do we care about regular matrices, regular transition matrices? In the case of a regular transition matrices, that steady state is going to first of all be unique, and second, every other state, every vector state will tend to it as n grows large. Alright, so here's the theorem. For this to be true, I need P to be regular, and you could try it with the first example with 0, 1, 1, 0. it's not going to work. You're going to have states that keep jumping around. It's not going to converge. So I'm going to assume that P is a regular matrix, transition matrix, sorry. First thing, there's a unique steady state so what that means is there's a one-dimensional eigenspace for E1, and when we ask that it's also a probability vector, we get a unique one. Second, for any probability vector, x to the naught, so any starting position, any starting repartition of the odds through the state, if you apply p enough, you're going to get that steady state that I forgot to give a name for. Sorry, let me put it in blue so you can see it well. So there's a unique steady state Q for P. And third, if you look at the matrix Q, big Q that we computed, which is the limit of P to the n, that matrix has first column Q, second column Q, third column Q, and so on. So it's just Q, 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 Q. So 3 limit as n goes to positive infinity, which we used to call big Q. So let me use big Q again to relate it back to the last example. So limit as n goes to positive infinity, P to the n, that's Q, Q, Q. And then it depends on the size of the matrix. In our case, it was a 2 by 2, so we only had 2 columns, but both were 2/3, 3/3, 2/3, 2/5, 3/5, 2/5, 3/5. That's hard to say. So in the next video, I'll be doing an example of finding Q without diagonalizing P, without finding P to the n, finding a real expression. I'm going to use this theorem. So I'm going to use the fact that it's a steady state as an eigenvector for lambda equals 1, and that's going to make the algebra much smaller, much easier. And if you think about it, even just to diagonalize the matrix P, you need to find eigenvectors anyway. So here we're going to find a single one and use this theorem to finish the problem.